So in this tutorial, I would finish these examples that we have done in the class before lunch, and then do another example for the induction, and then I would like to come to the give some example problems. I mean, those that were uploaded last week with a past exam, I would like to work through some of those. And of course, you also can ask with all these questions if there's something specifically that we should still address. So these were examples where the question was how, in what of these cases is there an voltage induced? And you see in this first example, we had a magnetic field that was oriented in Z direction. That meant for us it was out of the plane here. Yeah, the Z is going out of the plane. And you have starting, if you look at the magnitude of the magnetic field, then let's call that X, Y, and this is our Z here. So you have till here where these points start, you have basically a magnitude of the B field, which is 0, and then it has a jump, and here at that point it goes back to 0. And in this area in between, you have it constant. And as you move the loop in this direction here towards an X direction, let's call that, then at that point where it starts to enter here, that field, you start to build up a flux inside. And the flux is given by integrating over the area that is enclosed by this loop here, over this inside of this loop area, the magnetic flux density. Integrate over this area and it gives you the flux. So the total flux in the loop is obtained in this way, but you have to consider that your flux density can be position dependent and it can be also time dependent. And on top, also your area of your loop possibly could change. That was this example here where we are sliding that third wire and so enlarging that area here. And the induced voltage depends on the temporal change of the flux. So at that point of time, you're entering into this field. So gradually, more and more flux is penetrating here, that area, and you have a temporal change in the flux. That's why you have a voltage induced. And the same thing happens when it's leaving. Here, it is fully covered in the flux, but even while it is moving, the flux is not changing with time. So because there is no temporal change, that's why you have in the second, at the second point here, no voltage induced. And in the second, in this further example here, we are not moving the loop, but we have taken a B field, which is dependent on time. So it's B naught cosine omega t. And even though there is no motion of the loop itself, you still get an induced voltage because you have a temporal change of that magnetic flux density and hence also of the magnetic flux. And that's what is called then the motionless induction. Now we have here what is labeled actually with the case number 6. You have here a B field. You see that it shall be our X and our Y coordinate. The loop is moving, and the B field, however, it has only a Z component. Why is this is a set, right? This is just to make that clear. Shall be a set component. So now, do we have an voltage induced? Well, it remains always in the field where there is some, so there's always flux in there, but you see that flux is spatially dependent. You have this dependence on x. So as you're moving in x direction, the flux through the loop is also changing, and for that reason also here you have a voltage induced. Yes, since our B field is position dependent. This is position dependent on x, and the loop moves in x direction. Of course, it depends on the speed of the loop, how fast it is moving in x direction, how fast, I mean, the local gradient of the field, how strong it is, how strong the voltage will be induced. So the loop moves in x direction. Therefore, the phi that is inside the loop changes. So this is a motional induction. And what happens, for example, if we had now a seventh case where our B field is oriented in y direction? So y direction would be now, y direction is here upward. So then we see that there's actually, the B field is then not causing any flux through the loop, and hence there, even though it is changing, it does not impact. But let's make here, I want to change this problem. I don't want to make that EY. I want to make that E set. And if it had been directed in EY, then of course the flux would have been perpendicular to the normal component of the area, and so there would have been no flux through the loop. More interesting is actually the scenario where we have now a variation in of the B field, and it changes with the coordinate y, so y is upward direction, but it is also still oriented in z direction. Still, we will not get then any voltage induced because the y dependence is not of relevance if we move our loop in x direction. So also then our flux would be constant. So answer is also no, because the B is only y dependent and the loop in x direction. So phi is constant. So going back to case 5, we had our B being B0 times cosine omega t and everything oriented in z direction. Then the loop is inside the field. The loop is has a side length of a by a, so it is a square, and loop is at rest. That is for the assumptions. So the loop is inside the B field, loop side length of A, and it is a square. It is a square. And also the loop is at rest. Then we would like to calculate and graph the induced voltage. and draw the, sorry, you want to draw phi of r and u induced. So you get phi of A is by integrating over the area of the loop over the B field. And in that, basically, in the induced voltage is in the negative time derivative of the flux. And if you look at the loop, this one here is the differential element here of the area is the normal vector and the dA. Then you have, sorry, this phi can have a dependent on area and on time, but now we assume that we only have a time dependence. So that would be given then by the magnitude of B. It would be given by the size of the loop if it is oriented in alignment with the B field or not. That enters then here into A for the area. Sorry, A, we can use A. That's the square size of the loop. This is small a, I mean the area, this is small a squared. And then depending on the temporal development, we have this cosine omega t. So we have a squared times b cosine omega t. And if we have something which is not where the normal vector is not perpendicular, then the general formulation would be that your b is, you have to take the b times the normal vector and times the cosine that is prescribed on the for the angle between the b vector and the normal vector. That is the general formulation, and this is in our situation here 90 degrees. We assume that, and that's what we enter in here. So that would be the more general formulation, and then of course the area of the loop. So you see that there's a cosine dependence. So our flux starts here with a square b, and it goes to minus a square b at the lower extreme, and then you have here pi over 4, pi over 2, pi over 3, 4, and pi. And yeah, this is your time. So this is how your flux evolves under the assumption. And then the u induced is simply by taking the temporal derivative, was minus the temporal derivative of the flux, and that gives you minus a square b omega times minus sine omega t. And that means you have here a square b omega sine omega t. So your induced voltage is just following the cosine, the sine relation then, if your flux follows the cosine relation. Okay, let me get now to the tutorial part. Here, I mean, the next problem here would be that you actually have a rotation of the loop, and what you have to consider then here is basically that you make use here of the circumstance that the alignment of the B field with the normal vector is changing. So basically, you have a normal vector which having a temporal dependence, and that enters here if you have a rotation that is given that can be described by a cosine function, then you will have a normal vector that is dependent on cosine here. That would be for the next example. But let me get now to that tutorial, because there's also a problem with induction. I would like to deal with that. That is problem number 22. And after that, I would like to enter a bit into this examples from the exam 2019 that I've posted last week online. And maybe you have already tried to solve some of the problems. So then it would be good if we are working on this in this tutorial now. I think I removed that somewhere. Just looking for the problem statement. Just a second, I'll search that. Yeah. Where did that go? Oh, yeah. So you see here, this is a problem 22. You have two straight wires which are placed in the XY plane, and one of them is aligned along the X axis. This would be that one here, and the other one here is at an angle here, at an angle alpha. And then you have the third wire, like we had today in the example, we had two parallel wires and they're sliding the third wires in this X direction. Now you have two wires at an angle and you're sliding the third one. And the question is then, what is the voltage induced? You have here B field, which is constant in Z direction. That means it's pointing outward of the plane. You have X and Y here, and Z is pointing towards you. And as you move this third wire here with a velocity V in X direction, you're increasing the size of the loop. And as a consequence, there will be more flux through the loop present. So this is our problem 22. And what is the voltage induced? That is obtained by taking minus time derivative of the flux. Phi is the magnetic flux here. And that we obtain by taking the integral over the now time-dependent area over the magnetic field times the differential area element, the magnetic field, the magnetic induction here, or flux density to be more specific, that is only directed in Z direction. And the area element, you see we taking a loop here, starting here at the lower wire. Then our area element is also oriented in Z direction. The normal vector, you know, if you go counterclockwise, usually, and you have the right-hand rule that tells you which is the direction orientation of your normal vector. And then you have here B0 times A of t. And this here is in the end a motional induction here, because the loop, oh, yeah, I'm writing something. So this is problem 22. You take the induced voltage as a time derivative of the flux. You are integrating over the area, which is a function of time. B is constant in Ez direction. The area element is also in Z directed. And so you have here this motional induction, and your phi. What is your phi now? So if you're looking at the size of the loop here, you have an angle here, an angle alpha. This here shall be the length of the where the moving, I mean, starting from the origin till where you have the moving via segment. This is xp as used in the problem statement. And this here is at the right angle. And this is the yb, that is a connecting distance from the lower to the tilted wire. And you see that this angle, the relation between the two wire segments of basically this is xp here, this is this distance, and here from here to here you have your yb, and then you see that there's a angular relation that the tangent of alpha is equal to yb over xb. So your area that you have enclosed in this triangle is 1/2 xb times yb. And this xb, on the other hand, is given by the, it's a time variable quantity, so that is given by the speed that or the velocity of that wire in x direction times the time. And the yb is also changing because that is given by your xb times the tangent alpha. And that is velocity times time times tangent alpha. So this is what you use to get your time-dependent area. You have 1/2 times xb, that is v times t, times yb, that's again v times t times tangent of alpha. And now you can insert that. Then you have your phi is b naught times 1/2 v square t square tangent alpha. And your induced voltage is obtained by taking minus the time derivative of the flux and just plug in the flux as we have obtained here in the line above. So then you have minus b0 times 1/2 v square and tangent alpha times 2t. The t is being taken a derivative of. So you have in the front 1/2, in the back you have also a 1/2. So you get basically minus b naught v squared times time times tangent alpha. So that is your induced voltage, and that answers already question A. And now the question is the current that is flowing through the wire loop, I, and the resistor that is asked for. Now you see in that problem statement, we have, before we always had here an open port, but now, of course, we have still here a voltage induced, but the port is now, here there's a resistance connected in between those two. So you have also a current flowing here. The induced voltage we have obtained just now, and now we want to know the current that is flowing then there. Well, that is straightforward then, obtained by Ohm's law. You have the voltage is related to the current by the resistance. So then means we get I as a induced voltage over the resistance. The induced voltage we have there just in the line above. So this is minus B0 V squared T tangent of alpha divided by R. that is all that is asked for actually in problem B. And now the magnetic force acting on the moving sliding wire, that is the next question asked. So what is a magnetic force on the moving wire? So you have the force that is from the Lorentz force. We said that is depending on the current, and it depends on the orientation of the wire element, which is given by the length element del dl, vectorial length element, and the cross product. Yeah, this is L. And the cross product with the magnetic induction. So then this is what we stated here. This is on a short wire segment. The complete force on the wire we obtain by integrating along the wire over this differential force element. And that is, we are integrating for sliding wire, we integrate for y from 0 to yb. And the current here is, again, I. The magnetic field is B0. And the magnetic field is directed in, Z direction. And the current is, the line element actually is directed in y direction. So the line is in y direction, and the magnetic field is directed in Z direction, and we integrate here over y. And then if you are taking the right-hand rule, Ey cross Ez gives you Ex, and you can always quickly also verify that with your if you have a cross product, the direction with the right-hand rule. If the first one in the first element here gives you what you align with your thumb, this is what you align with your index finger, and then the resulting is the direction your middle finger points to. So this is basically your differential line element dl. And you take here the cross product. This is your B field. So you will obtain the E and the B can be pulled out of the integral. So we have to integrate from 0 to yb, and basically just over the constant. And the yb, however, keep in mind, is this v times t. This is velocity times the time times this tangent alpha. And this integral just gets us 1 times b times, it is oriented in x direction. So the total magnetic force, we plug in now the E, the I is what we have computed in problem B. So this part we plug in, and we plug in the B field, or the B. So that gives us minus V square T B times tangents of alpha over R. This is the current that we calculated, times B, that is this B here. Yeah, this B. And now we plug in also the YB, and that we have here on the side. That is then times V times T times tangent of alpha in the EX component. So that's all that it takes. We have the minus here, b square. No, sorry, that is then we collect all these terms. This is v to the power of 3 times t square times tangent square alpha. So we just collect all the terms over r, and it is directed in minus ex direction. So that's problem 22. And now you have questions? We could further expand this problem by, for example, making also our E field now time dependent. But I would like to get to the exam problems now, because I think that might interest you in particular. And you see here one of the problems. So you have here, this is an electrostatic problem. You have two discrete charges. The one is called capital Q1, and it is a small q electric. It is located at position R1. The second one is called capital Q2. It's of the same charge amount as the first one, and that is positioned at R2. Both are in vacuum, and both are larger than 0. Your R1 is given as 1 for X, 2 for Y, and 3 for Z component, and the R2 is 1, 2, and minus 3. And now you want to have the electrostatic force applied. What is an electrostatic force which is applied on a point which has now the negative charge minus QEL, and it is located at the position R000, so right here at the origin. And we want to obtain an expression then also for the E field. So first we want to have the force, and the force on this small charge Q you obtain by using Coulomb's law. And you can use the superposition. That means you have 1/4 pi over epsilon naught here times Q, that is the charge in the origin. And now use the superposition principle. You have here for the first charge Q1 over R1 squared. Sorry, you take here to the power of 3, R1, the power of 3. Becomes easy now because, for your R here, you have to actually, if you be more precise, because you might want to calculate it somewhere different, but at the origin, you are taking here R0 minus R1 to the power of 3. And here you put in, you put in there also R0 minus R1, but R0 is just 0, 0, 0, and R1 is 1, 2, 3. So basically you get here minus 1, minus 2, minus 3. And you take the second charge, Q2. That is here applying the superposition principle. You see both of them are multiplied with 1 over 4 pi epsilon times the test charge here. And here you get then minus 1, minus 2, and plus 3. And this charge Q here becomes minus QEL. The charge Q1, but also Q2 are plus QEL. So you get here minus QEL squared over 4 pi epsilon times. And you see what's here, and you obtain 14 to the power of 3 square root and to the power of 3. And -1, -2, -3, plus -1, -2, +3. You see, both R0 minus R1, but also R0 minus R2, they are of the same magnitude. And you obtain the magnitude by squaring each of these components. So 1 squared is 1 plus 2 squared. This is 1 plus 4 plus, that's 5, and then plus 3 squared. So you add another 9, so you get 14. And then you take the square root. That gives you, that's how your 14 comes about here, yeah? And this one here, this is actually -2, -4, 0. So you can write then that your Q electric squared over 4 pi epsilon naught, 1 over square root of 14 to the power of 3. And the minus we pull in here. We had -2, -4, 0, that we make 2, 4, 0, yeah? So this is your force. You have it by magnitude and by direction. So you have the complete force vector here on the test charge. And what is the electric field that you obtain at that position? That is obtained by taking the force divided through the charge of the test charge. And that means we get here minus Q electric, because it's not squared anymore. We have taken one out, and we have also the minus brought it back here. 4 pi epsilon 0 square root of 14 to the power of 3 times 240. Are you fine with that? Yeah. Get the what? Square root of this 14. So you see here conveniently, you have that around the origin. If you're very accurate, you want the distance vector, you take the difference between the vectors. This you can actually drop also because the R0, because this is all at the origin. But you might want to know the field also somewhere else than in the origin. So then you would need to form the distance vector here. But then if you look at this one here, how do you obtain that? Well, that is a absolute, that's a norm here of -1, -2, and -3, right? So you take here -1 squared plus -2 squared plus -3 squared, add them all up. I mean, you take the square of each of these components, and then 1 squared is 1, plus 2 squared is another 4, plus 3 squared is another 9. So this gives you 1 plus 4 plus 9 is 14. So in general, if you have any R, and that gives you here some X, some Y, some Z, then if you take the absolute value, you get X squared plus Y squared plus Z squared, yeah? This is the norm of your vector. So now determine the electrostatic potential, which is generated by the above given charge constellation at the position. So there you can make use of the Coulomb potential. We know the Coulomb potential, but we haven't ventured for that into so much detail, but I want to show you nevertheless. The Coulomb potential is the potential that you obtain from a single point charge. And also there, you can apply the superposition principle. And that means you can do here a summation of the individual charges which are contributing to the Coulomb potential. And this here is now the other phi, the phi that we were talking, that is the electrostatic potential. This is not the flux this time, this is the potential. But if you wonder, if you have any problem statement, it will say electrostatic potential phi. Will never say determined phi generated, because you have to say what phi is, you have to specify. You cannot just write determined phi. You have to say what phi is supposed to be. So there's no chance for confusing that really in a problem statement, because if you were thinking this is a magnetic flux, it wouldn't get you anywhere here. This doesn't fit in here. But there's also no concern because it says electrostatic potential. So this phi is electrostatic potential. So now question number 2, it says state Gauss's law in integral form for a continuous charge distribution with space charge density rho of r. Gauss's law, that I hope you know by heart now, that is closed surface integral over the electric flux density. What's on the other side? You know, Gauss's law. What is on the other side? Huh? Integral? Yeah. It's a row, you probably mean, yeah. But yeah, it's a row, yeah. But you're right. Yeah, it is d. You have, or dv. You can also write dv, or if you take r, then you make to the power of 3. Yeah. So this rho here is a space charge density. So you're right. It looks very similar to a p, but it you have to look. Especially, it depends on the font type you're using. Uh, it can look slightly different, but it is a row. So, in other forms of to express it in a different way. I mean, it could be potentially, but here, yeah, you have to give it an integral form. So you have, I think you have those also on your formula sheets. Gauss's law, you have it in integral and you have it in differential form. It's not on the different, but is it not on the formula sheet? Well, I'm thinking it's also there, but in differential form, you just have it here. Then you write. You don't have that on the formula sheet? I have to check. But anyway, the formula sheet is set, but I thought that it's also there in differential form. I think at least that the combining one, I think it is also given in differential form. But I guess, yeah, that integral form is more visual in that sense. Actually, anyway, here yeah, it is asking then in the next question, deduce a differential form. So if you want to deduce a differential form, then you would take here the volume integral over the divergence, and then you would get here the volume. There, basically, you have to know that you can, instead of taking the instead of taking the volume, instead of taking the closed surface integral over the flux density, you can write this is the volume integral over the divergence. So if you now shrink here the volume arbitrarily small, then you can conclude that this still holds true. Then eventually the divergence of D becomes the space charge density. What is also important to know the units of these quantities. So in terms of units, flux density. You know the unit of the flux density? So that is Coulomb per meter squared, or ampere second per meter squared. I think this is important that you kind of have these quantities also in your mind, because then you also may know whether what you're writing makes sense, whether what you have on the, if you have Gauss's law and you integrate here over space charge density, and you know that this is charge, so basically Coulomb per cubic meter, and you integrate over volume, then you end up with having Coulomb. And then here you see you're integrating over a surface. So you also should, in the end, have the same unit on that side. And here you have ampere second per square meter, and you're integrating over square meter. So if you know also the units for all these fields, it's really helpful, because you know then whether what you're doing is really consistent. Yeah. So take a look at the units, then it tells you, are you doing consistent work? Because if the units are not matching, then you know there's something wrong. So the rho is Coulomb per cubic meter, or ampere second per cubic meter. On the other hand, just remember that we also said we could use D and use it for, if we have the D field on an interface, it gives us a surface charge density. Remember, sigma, it's a sigma, and the surface charge density has a unit of ampere second per square meter. That's just the same as the electric flux density. Sorry? Yeah. This one here? Yeah, thank you. Thank you. That I left out, yeah. That is correct. Now we have a problem with a capacitor. Where did it go? You have the problem at your hand, the question 3. You have it on your problem sheet, the question 3, because apparently I didn't copy it right now. I mean, I have it here, but you have it also with you, the Q3? Okay, I'll copy it then in later. But the question 3 is consider two plate capacitors whose interiors are partly filled with air and partly filled with a dielectric medium with permittivity E1. According to the figure below, both capacitors have an area A, and the height of the respective dielectric layer is H. So we have here the capacitor 1. It has a dielectric E1. It has a height H and electrode surface area of A. And the other one is also a parallel plate capacitor that also has electrode size A, and it has it's filled here with an permittivity, a dielectric material is permittivity epsilon 1, and the other one up there epsilon 2, and the height is H for each of them. So now calculate the capacitance, is the question. Calculate the electric capacitances C1 and C2. So C1, we know the parallel plate capacitor formula is given by taking the permittivity. It becomes also here, you can very easily remember that, the capacitance. You can very well visualize if you have a parallel plate capacitor, the larger your electrode plate is, obviously you can store more charge than, isn't there? Because you have two large plates, so you have a lot of area where you can put on charges that can attract each other. So larger the area, the larger the capacitance. At the same time, it is helpful if the two plates are very small. I mean, the separation is very small. The further you put these plates apart, then the capacitance is reducing. So you have this is a formula of parallel plate capacitor, and this is for the first one. You have epsilon 1 times A over H. And then for the second one, you have, well, you have a series, we could call it C2A in series with C2B. And let's think of that being, now you can take the equivalent circuit that we have derived here in the class for if you have a layered capacitor with two layers in series like here, then you have here your, this is your capacitor C2, and you can split it up in a capacitor C2A and C2B. That would be epsilon naught times AH. That would the capacitor C2A, and you want to have it in parallel now with the, sorry, you don't want to have it in parallel, you want to have it in series. I'm using the wrong notation. And you take this one in series with the second one. So what is a series connection? For the series connection, so basically, if you give it in C2, so let me give it like that. This is if you connect these two in series. That means you add all the inverses, gives you the inverse of the total capacitance, yeah? So that means your C2 becomes, that's what you meant, isn't it? So we can write that then as A over H, E0 times E1, E0 plus E1. So this is a series connection of the two layers that are forming then our capacitor C2. Okay, now we have that. We have some capacitors connected in series and in parallel. This is our E naught, E epsilon 1. This is our capacitor C2. And we have another capacitor C2 connected here. And then on the other side, on the parallel line, we have that capacitor C1. And we have a voltage U naught. Now the question is calculate, not sure why we have here again B, but the question is calculate the total capacitance, total, C total. So C total is, now you see C2 in serial with C2 plus C1. That in parallel case, you just add up the capacitance. But serial, you get the inverse of the capacitance value of the, by adding the inverses of the individual unit elements. So you get here 1/2 C2 plus C1, and that is here 1/2 A over H, as we computed in the previous example or part of the problem, E0 plus E1 plus E1 A over H. And then the question is, not sure why that was denoted with B again here, but to keep consistent, I rewrite that here. Now calculate the electric field energy. Calculate the electric. And that would be V electric is 1/2 times the capacitance, of course, of the total one, times the voltage that is being used to charge up this capacitance. And that would be then 1/2 epsilon 1 over h plus 1/4. Okay, that is also quite simple then. And now question 4 is now we consider a conductive material. We consider now a conductive material which is containing a certain number of mobile charge carriers. This is our question 4. Each of the mobile carriers has a charge Q. The particle density of the mobile carriers in the material is n, the small n. Under the action of an electric field, the carriers move at a mean drift velocity v. Calculate the power which is delivered by the electric field to one single mobile carrier. So we have here the power density, that is a small p, that is given as the current density times the electric field. Now you can also make the sanity check. What are the units? Power density is watt per cubic meter, and your current density is ampere per square meter, and your voltage is voltage per meter. So that gives you a volt ampere per cubic meter, and volt ampere is watt. So the units are all matching. So this is also given as Q, that is a charge value of a single carrier, the particle density, so that Q is given as an ampere second, N is given as parts per volume, so in 1 over cubic meter, times velocity, that is given in meter per second, and times E, which is given in volt per meter. Then you have the total power. This is capital P. That is then Q times velocity times electric field. So, and then what is asked for, calculate the power delivered by the, okay, that we have here. And now for one, so this is the total power, but this is yeah, but this is the total power for one charge carrier. Yeah, and that is also what was asked for. Calculate the power delivered by the electric field to one single mobile carrier. So remember, N is the charge carrier density. That is basically a number per volume. N is the charge carrier density. That is the number of charges, number of charge carriers, and this is per volume. In the power density, actually, that we also have given already in the problem A, the power density is, that is however now taking into account the total number, but we also take it per volume because we have added the carrier density. Q5, this is state the charge balance equation in differential form. So in differential form, it means that the d rho with respect to time plus the divergence of the current density is vanishing. That you remember the charge, change of charge with time is equal to minus the divergence of J. So that follows immediately then this here follows the balance equation. And remember also that the current is, if you look at the more macroscopic view, the current is given as a change of charge over time. And here you have that equates here basically on a local form to the current, and this one here to your charge. But these we work with local quantities and work here with densities. This is more the integral or the global formulation. So your current is given by the temporal change of charges, and that results in this charge balance equation. That is always true. And now show by calculation that the electric current density, the current density shall be given here with 2 times C naught is a function of y and x, and it is directed here in x direction, and it has a second component that is directed in y direction, that is given also by the constant times y square, and this constant C naught is larger than 0, and you want to see that it fulfills the stationary charge balance equation. So your current density vector is given here. You can write it in this in a column vector. C naught is larger than 0. And now we want to see what the partial derivative of the space charge density